Hello and welcome to a lesson on permutations, which I managed to spell correctly here and then misspell here. I forgot a letter in that, but what is a permutation? So a permutation is what we call an ordered arrangement, okay? An ordered arrangement, more specifically, it's an ordered arrangement of items, things, people, whatever it is, that occurs when none of the items are used more than once. So items are not used more than once. And it's really important to know or to note that the order matters. It's an ordered arrangement, okay? The order of these arrangements matters. Particularly because in the next topic we're going to talk about what happens when the order doesn't matter. Now, we're still looking at options for things, so multiple options for things, and then finding a total number of combinations is really similar to what we were doing with the counting principle. In fact, we can still use the counting principle, which means we can still multiply. We can still multiply the number of ways that each outcome can occur to find the total number of outcomes in a situation. So I'm going to show you how what we're doing is connecting to the counting principle that we've already talked about, and then I'm going to show you how we can use this concept of permutations and actually a formula to simplify our work. Now you'll still have both options. I just want to throw out there what some of the language and what options are going to be available, and then you sort of choose what works for you. Okay? So here's our first example. It says you need to arrange 7 of your favorite books along a small shelf. How many different ways can you arrange the books, assuming that the order of the books makes a difference to you? So let's just kind of list out what we're doing here. On a shelf, we're going to put book 1, whatever our choice is for the first book, and then we'll put the second one, and then the third one, then the fourth, then the fifth, then the sixth, and then the 7th book. Okay? So we have books 1 through 7 that are going to go on a shelf. Now, I can't put one book in more than one spot, right? And apparently the order in which I put these books makes a difference. So how many options do we have for each of these spaces? What is the number? Let me not change colors yet. What is the number of options for each of these books? Well, when I go to put the very first book on the shelf, I have all 7 books to choose from, right? We've got 7 books here that we're choosing from. So all 7 could go in this first spot. But once I put one in that first spot, in the second spot, there are only going to be 6 left to choose from. And then I've placed 2 books, and there's only 5 left to choose from here, and then only 4 left here, and then 3 left here, 2 left here, and when I go to put my last book on the shelf, there's only 1 book that could go in that spot. And so using the counting principle, we would multiply all these out, multiply all that together, and I'm going to absolutely use my calculator for this. 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. So there are 5,040 different ways I could arrange these books on a shelf. Okay, not so bad, right? So this is an example of a permutation. It's an ordered arrangement of 7 books on a shelf, and I cannot use any of the books more than once on a spot on the shelf. Okay? So we use the counting principle like we did before to find the total number of arrangements. Alright, let's try that again. So you're a Little League coach. Congratulations. You have 13 players on your team, and you need to pick a lineup with 9 players, because in baseball only 9 players can take the field. So order is going to matter when you make this lineup, right? The person who bats first versus second versus third versus fourth, they're all different, so the order matters. How many batting orders can be formed? So what you have, again, is the first batter, and then you have the second, and the third, and the fourth, and the fifth, and the sixth, the seventh, the 8th, and all the way to the 9th batter, okay? So let's talk about the number of options for each of these batters, okay? There's 13 players on this team. So when you go to choose your first batter, your first guy in your lineup, guy or gal in your lineup, all 13 players could technically be chosen for that first spot. Now, but once you've picked someone for the first spot, there's going to be 12 left here, and then every time we're going to decrease by 1 because you've placed someone on the lineup. So then 10, then 9, then 8, then 7, then 6, and then 5 left here. And there's persons 4, 3, 2, and 1. Those last 4 not going to get on the field here unless they sub in, okay? So we're going to multiply all these and figure out the total number of lineups that can be created. So 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 is a gigantic number, but here it is. 259,459,200 different lineups are possible. So again, this is an example of a permutation problem. You're looking at an ordered arrangement of players on a lineup. The order of the arrangement matters, and you cannot put one person into more than one spot on the lineup. And we use the counting principle to show there's 259,459,200 different lineups that could be created, right? No pressure for the coach there. Okay, now I want to show you another way to calculate these things we're calling permutations, but it's going to involve us knowing some other notation. So I want to show you some notation before I get to that permutation stuff. Okay, so this notation that I'm talking about is called a factorial notation. So if n is a natural number, we've talked about natural numbers, remember those are the counting numbers. So if n is a natural number like 1, 2, 3, 4, 5, 6, and so on, then this n with a little exclamation point, we read that as n factorial. And what it means is it is the product of all natural numbers from n down to 1. From n to 1. Okay? So for example, here we have 6 factorial. That means find the product of 6 and all of the natural numbers before it. So the product of all natural numbers from 6 to 1. I guess I should say down to 1. From n down to 1, or 1 to n, either way. So 6 factorial means take 6, multiply by 5, and 4, and 3, and 2, and 1. Or vice versa, right? 1, 2, 3, 4, 5, and 6. So 6 factorial is going to give us some value, okay? Now, what's handy is, and this would have helped us previously, when we calculated the number of arrangements for books on the shelf, we did 7 times 6 times 5 times 4 times 3 times 2 times 1. We could have just said that's 7 factorial. And we don't have to type all the numbers into the calculator. So here, for example, I could just type in 6 and then go to my keyboard and find the exclamation point. And it is missing from my... There it is. I have to shift. I have to give a shift, but how do I do that? Nope. Shift. There we go. I have to shift and get, because my keyboard is shrunk there, it's on top of the percent. Okay, so 6 factorial is 720. And just to show you, if I typed in 7 factorial, that's what we used earlier. 7 factorial, 7, and then shift. No, I said shift. There we go, is 5,040, and that was the answer we saw a bit ago. Okay, so then 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But if I wanted to actually figure out how much it was, I would just have to type in an 8 with an exclamation point, and the calculator would tell me it's 40,320. Okay, or we could make a fraction out of this. So 12 factorial would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1. And again, I could put all that individually into the calculator, or I could just put in the actual notation into the calculator, but what you're going to see is this stuff all canceling out here, right? That's what happens when a fraction has something in common in the numerator and denominator. So really I could type in 12 times 11 times 10 times 9 times 8, and let's just verify. 12 times 11 times 10 times 9 times 8, or, so 95,040 is what I should get. I can just use the notation. So I'm going to hit the divide button to give myself a fraction, and I want 12 factorial on the top, and I want 7 factorial on the bottom. And there it is, same exact answer, 95,040. Okay, so 95,040. And it's going to occur in some of the work that we do, so I just want to give this to you now. 0 factorial is a little interesting. 0 factorial is defined for us as 1. So if we encounter a 0 factorial, it is 1. Not that you have to remember that, because you could again use your calculator. It will tell you that 0 factorial is 1. Okay, but that's going to be useful as we progress here. Okay, so now, what does this have to do with permutations? Let me try to show you. So a formula for permutations is available, and again, it's supposed to simplify some of the work that we're doing. So we have this formula, again, a shortcut for the calculation of permutations. It is a number of ways in which the number of permutations, so again, ordered arrangements of R items taken from a group of N items, and again we know that none of the items can be repeated. So this is notation for permutations. Okay, when you're reading this, N is the number of things you have to choose from in your group, so the total of choices in the group. And then R is how many you're actually choosing. Number you are choosing. So for example, with the 7 books being arranged on a shelf, you are choosing all 7 books from the 7 that there were to choose from. So just using notation, that's the number of permutations when you're choosing 7 books from a group of 7 books. Okay, or the players on the lineup. We were looking for the number of permutations when we were choosing 9 players out of the 13 that were available to choose from. So that's what the notation would look like. And according to this formula, we can use this formula to calculate that number of permutations. So let me just show you here, and you don't need to write this because I'm going to show you some things in a second. But according to this formula, if we were to find the number of permutations when you were arranging 7 books, choosing from a group of 7 books, on the top of the formula, notice here, is n factorial. So n factorial, so that would be 7 factorial. And then on the bottom is n minus r factorial, so this would be 7 minus 7 factorial. Okay, so 7 factorial on the top, and then 7 minus 7 would be 0 factorial on the bottom. Well, 0 factorial on the bottom was just 1. So 7 factorial is going to get us our answer. Now that's what we got, right? We used the counting principle to do that. What this is showing us is another way. Now it's supposed to be a shortcut, and maybe that formula doesn't look like much of a shortcut, but in fact it's going to be. But I just want to do a little more explaining and comparing of this formula to using the counting principle. So I want to go from our note sheet for a second here to show you. Okay, so we had this arrangement of 7 books with the counting principle. We said book 1, 2, 3, 4, 5, 6, 7. There were 7 options, 6, 5, 4, 3, 2, 1. We got 5,040 arrangements. So now with our permutation formula, we would say, what's the number of permutations when we're choosing 7 books from a group of 7? So the formula says n factorial on the top. Remember, this was n here, and this was r here. So we're supposed to have n factorial on the top, and then n minus r factorial on the bottom. Okay, so n factorial on the top would be 7 factorial. N minus r would be 7 minus 7 factorial. So 7 factorial on the top over 0 factorial. Well, that's 7 times 6 times 5 times 4 times 3 times 2 times 1, and this is just 1. So we're going to end up with the same answer. This is just another formula for arriving at that answer. Okay? Let me show you again, and then I'll get to the real how this simplifies life for us. Okay? So the second problem, we looked at the lineup. We were choosing 9 players from a group of 13 players. So we would say, what's the number of permutations when you're choosing 9 players from that group of 13? So we're supposed to have, remember this is n, this is r. It's supposed to be n factorial over n minus r factorial. So n factorial would be 13 factorial, n minus r would be 13 minus 9 factorial. So what happens here is we have 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Not what we had in the answer because we stopped at 5, right? Well, this is why we need the n minus r factorial on the bottom. So 13 minus 9 is 4 factorial on the bottom, right? This is 4 factorial down here. And 4 factorial would be 4 times 3 times 2 times 1. And what happens is the 4, 3, 2, and 1 cancel, and we are left with exactly the same calculation we made using the counting principle. Okay, now that formula might not look much easier for you, but in fact it is, because we don't actually have to use the formula. We don't even have to know the formula or memorize the formula. We just have to be able to use Desmos. Desmos will actually do this calculation of the formula for you. So if you understand you have a permutation, you can just punch something in the calculator. So all you really need is Desmos. So let me show you how to do this in Desmos. Clear all this out. So if I wanted to calculate the number of permutations, choosing 7 from 7, which we knew was going to be 5,040, we're going to go into Functions, choose Stats, and then this NPR button, okay? So on my keyboard here, I'm going to go to Functions, I'm going to go to Stats, and then down toward the bottom I see this NPR. And NPR, the notation looks a little different here. So on paper we write NPR like this. In Desmos it says NPR, and then it gives you this little parentheses, and what it wants you to put here is N comma R. So what we're going to put here is 7 comma 7, and then it gives me the calculation 5,040. So I don't actually have to do all the work with the formula. I'm just going to plug numbers into plug it into Desmos. Okay. Same thing with the second one. So functions, the stats is already there now. NPR. If I wanted to know the number of permutations, choosing 9 from a group of 13, I'm going to go 13 comma 9 here, and then it's going to give me that 259 million number that we calculated before. Okay, so all we really need to know is how to put this in Desmos, and there we have it. We're going to put the n and r in parentheses, and it's going to make the calculation for us. That is a lot simpler than having to write out any of the factorials or anything else. Okay, so let's try a few. Oops. Let's try a few using this notation. So you and 19 of your friends have decided to form a business. The group needs to choose 3 officers, a CEO, an operating manager, and a treasurer. And how many ways can the offices be filled? So this is a permutation. You're looking for an ordered arrangement of, see, a CEO, a manager, a treasurer. The order you choose these people matters, right? Once a person's a CEO, they can't be someone else, and so on. So this is a permutation. And what we're choosing is 3 different officers from a group of, this was 20 total. So we're choosing 3 officers from 20 total. So this is going to be a simple calculation now, just using our Desmos. And since I already have this here, let me just retype. There's 20 to choose from. We're choosing 3. That's going to be 6,840 different ways. Okay, now, if we wanted to use the counting principle, we absolutely could here. If we wanted to use the counting principle, we could say there's 20 ways to choose the first one, 19 ways left to choose the second, 18 ways left to choose the next. And guess what? 20 times 19 times 18 is going to get us that exact same answer. So if you're more comfortable with that, then do that. Although it's going to get tricky when we get to the next topic. Okay, so if you can identify this as a permutation, that's going to be, I think, easier. So let me just, if we wanted to use the counting principle, works the same way. All right, how about the next one? It says there are 15 people competing for gold, silver, and bronze medals in an Olympic event. How many arrangements of winners are possible? So this is a number of permutations. The order in which these people place in the event matters, right? So we're trying to get gold, silver, and bronze medals. That's 3 different medals, 3 different winners from this group of 15. So it's a number of permutations when we're choosing 3 from a group of 15, and that is 2,730 different ways. And again, if I wanted to use the counting principle, I could say, well, the counting principle, I could say all 15 people could have got the gold. There'd have been 14 left to get the silver, and then 13 left to get the bronze. And guess what? 15 times 14 times 13 is going to get me the same answer. Okay, so using the counting principle, we could have got the same answer. All right, now I want to show you here what happens if we have duplicates. So typically for permutation, we don't have things being used more than once, but if we do have duplicates, what's going to happen? So let's just look at the number of permutations here. If you were going to rearrange the letters, how many ordered arrangements of the letters in TWO are possible? So this would be, what I'm asking is, what are the number of ordered arrangements, permutations, if you're going to choose all 3 letters from the 3 that are there? Okay, how many different arrangements could you make? Well, let's see. If we're looking for permutations, choosing 3 from 3, we're going to get 6. So 6 permutations here, and what are they? Well, let's see. One arrangement of the letters is what we started with, TWO. Or we could go TOW. Or we could go WOT or WTO. Or we could go OWT or OTW. Okay, there's all 6 ordered arrangements. Now, what if we take the word to but spell TOO and try to come up with ordered arrangements there? Well, obviously TOO is an arrangement. We could go OTO as an arrangement. We could also go OOT as an arrangement. And that's it, right? I can't come up with another unique arrangement. Although technically this should have been P3P again, right? We're choosing 3 letters from the group of 3, but that's only something we can do if there aren't duplicates. If there are duplicates, what's going to happen? Well, this time we had 6, the first time over here, we had 6 arrangements. 6 arrangements. And over here, we only had 3 arrangements. And that is because if we have something that repeats, we have to divide out how many times it repeats. So this should have been 3P3 like we had before, but we want to divide out or divide that answer by 2 because the O here repeats twice. So if I took the 6 and divided by 2, then I would end up with the 3 arrangements. Okay? And that's not something that you would be expected to know. It's just like, that's the formula. All right, but this is sort of what's happening with the formula. So the number of permutations of let's see, n items where p items are identical, r items are identical. Let's go in order here. P, Q, R, and so on, is given by this formula. So whatever your total is, this is the total on the top, it's going to go here, and what you're going to do is you're going to divide by the number of times anything repeats. So these would be repeaters down here. Repeaters. And that's going to get in my way later, so now I got to move it. Okay, so these are repeats. Alright, so let me show you, because this might sound a little complicated right now, but it's actually pretty straightforward. So in how many distinct ways can the letters of the word Mississippi be arranged? This is technically a permutation, ordered arrangements of the letters, but we have some repeats here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So 11 total letters. So on the top of the fraction, we're going to have 11 factorial. And then on the bottom, we have to divide out repeaters. So when I say repeaters, I mean like the I. 1, 2, 3, 4. I happens 4 times. So I'm going to divide out a 4 factorial for that I that repeats 4 times. And then what else is repeating? Let's see, 1, 2, that was 4 I's. Okay, S is obviously repeating. 1, 2, 3, 4 S's. So I'm going to divide out another 4 factorial for the S that repeats 4 times. And then P happens twice. So I want to divide out a 2 factorial for the P that happens twice. Okay? And this is going to give us the number of ordered arrangements that divides out those duplicates. Okay? So calculator time. Let me delete all this out. So make a fraction, and we're going to put 11 factorial on the top. And on the bottom, we're going to put 4 factorial, and I wrote them next to each other here, but the calculator I think is going to want you to put multiplication. So we're going to put in another 4 factorial times another 2 factorial, and there's our answer. 34,650. 34,650 arrangements. Okay. All right, there's one last one here. If you want to give it a shot, feel free to pause. Otherwise, let's see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters again. So 11 total letters. So we're going to go with 11 factorial on the top. And then we have m happens twice. So we're going to divide out a 2 factorial for m. And then we have t happening twice. So we're going to divide out 2 factorial for the t that happens twice. A happens twice. Not sure why I skipped that one. So let's divide out a 2 factorial for the a that happens twice. And I believe that is it for repetition. So now we can divide out. Now I'm just going to use a little shortcut here. Let's go ahead and change that to a 2 and change that to a 2 so I don't have to retype everything. And now we have a bigger number. 4,989,600 different ordered arrangements of the letters in the word mathematics. Not just straightforward permutations, because there are repetition of letters. If it was a word where the letters didn't repeat, then it would just be permutations. And again, just to clarify, let me go back here. Right? If I said, how many ways could we rearrange the letters of the word to, T-W-O, that's just permutations. Straightforward permutations. We rearrange all 3 letters from the group of 3. But if there are letters that repeat, we're going to divide out those repeaters. Okay? Hopefully that makes sense. And if not, when you're working through your practice, then just feel free to reach out. As always, guys, I'm here to help. All right? Take care.